Okay, so we just go back to finish the final topic in these chapters. So the final topic is the stability problems. Okay, this is our final problem for hydrostatic. Because the stability is means if you put one particle inside the liquid or just the particle floating on the water surface. So can you just predict the stability problem for the particle? Okay, so the idea is we need to understand the relative positions of the center gravities. So when I say the center gravity is G in here, is the G point in here. And the second point is centroid of displaced volumes of fluid. Okay? But you can also call it is the center of Bouillon. So we use the C point here. So the idea is why we tell you, you just notice that the relative positions between 2 points. Because for these questions, you see, this is the force directions is upward. Because this force is Bouillon force. And another force is downward. Because this force is from the weight. And if you do some, you take a look, you connect 2 points, so you have a line cross over 2 points. But if the line directions is parallel to the force directions, that means in this distance there is no moment. There is no moment. But if you go to see the example shown in right hand side here, again you have the Bouillon force and the weight. But there is the line connection 2 points. So it's actually the line directions is not parallel to the force directions. So the particle should be rotated, right? Because there is some moment inside. The moment inside, like these directions, clockwise directions, rotations. So the particle will rotate. So the idea is quite simple. You just take a look and you find out the C and G point first, and consider the directions of the force is parallel to the line direction or not. If not, the particle should be rotated. Okay, so right now we just take 2 examples like the ship. So we have the ship just floating on the water surface, and again we have the C. C is the center of the Bouillon, and the G is the center of the gravities. So the idea is quite simple. If you see the ship in here is stable, right? Because no rotate. But why it is stable? Because the force directions is parallel to the 2 point connections line. Okay? But the idea is if you take a look for the point in left and the point in right, because in these regions is immersed into the water. So here we have the upward force. This upward force is, we call that is the Bouillon force, right? And then we have the rotation axis in here. Rotation axis here. So the moment contribute from this point. You just do the cross. You use your right hand. So you do the cross. the moment should be the negative moment, like these clockwise directions. But if you take a look in right-hand side, again, this is rotation axis, but in here, the force also upward for the buoyant force. And in that case, the moment should be the counterclockwise in here. So that's I use the sentence showing here. The volume to the right produces the positive moment, but the volume to the left produces the negative moment. And so one side is a clockwise moment, and another side is counterclockwise moment. So like to make the balance. So the ship cannot rotate, just stay here. Okay? But in case we just push the ship, and at that time point, the ship will rotate immediately. And then you see, in that time, we observe the C point and G point. The force direction is here, but the offset of the 2 points is not parallel to the force direction. So the force will go back to the stable conditions. Why I say that? Because you see, this is a force upgoing, and this is a force downgoing. So the rotation moment is counterclockwise. So that will move the ship back to the stable conditions. This is a normal physical phenomena. So if you push the ship, and the ship would like to go back to the stable conditions. So that's why you can see the moment like these directions. Okay? So, but the idea is, can we predict the stability problem for the ship? So I just write down 4 steps. The first step is just follow the 4th step, and you can predict the stability problem for any ship or any particle just floating on the waters. So first, the questions tell you the step 1, maybe your ship may rotate with the alpha angles. So like the angle showing here. So the ship rotates the alpha angles. And before the ship rotates, we know the C is the centers of the Bouillon force. And because you rotate the alpha angle, so the center of the Bouillon force just shifted to the C prime here. Okay, so this is for the step 1. And then you just along the C prime, you do the vertical lines. And you will find out the end point in here. The end point here. So we define the end point is meta centers. It's the meta center. It's very key parameters for predictions of the stability problems. So right now you have the end point in here, and then you just take a look at the step 3. If the M is above the G, if the M is above the G point, okay, and then along the G axis, the moment will counterclash rotations. And the step 4, in other words, if you put the G point beneath push the M point beneath the G, and then the ship will rotate along the G axis with the clockwise moment, and then the ship just immerse it into the water. Okay, so the idea is you just take a look GM, the connection line of the GM. If the line distance is positive, so the ship is stable. If the Gm value is less than 0, so the ship is unstable. So the idea is quite simple, because if you rotate the ship with a large angle, that means alpha angle increase. If alpha angle increase, the ship will rotate along these directions. In that way, the end point will going down. So in case the end point is beneath the G point, and then the ship will totally rotate and emit it into the water. So the idea is very simple. We just have ideas. We just predict the Gm distance. If the Gm distance large than 0, and then the ship is still stable. But the Gm distance less than 0, the ship is unstable. So our key question is, can we determine the Gm distance? If we can, and then we can predict the stability problem of the ship. Okay, so this is the idea. But usually it is very difficult to directly to compute the Gm distance. So right now we have the idea. If we know the CG distance, where is the CG distance? In here. And if we know the CM distance, the CM distance in here. Okay? So if the CM, you know the CM distance, and then minus the CG distance, should be equal to the Gm, right? So in that way, if we can determine the CM distance and the CG distance, and then we compute the minors, and then we exactly know the Gm is less than 0 or larger than 0, and then we can predict the stability problem of the ship. Okay, so but we until now we didn't know how to compute the CG distance and the CM distance. So our purpose is we would like to know the CG, or we would like to know the CM. In that way, we have the CG and CM distance, and then we can compute the Gm value. Okay, so go back to the ideas. So the ideas is based on the moment balance. Okay, so again we have the x bar. X bar is the distance between the C and the C prime. And then we multiply the volume. The volume here is displaced volumes. Displaced volumes. Okay? And then we know the gamma is the liquid specific weight. The gamma multiply the displaced volumes, and then we can compute the Bouillon force, right? FB, okay? But because the left hand side and the right hand side, we have the same gamma, so the gamma cancel out. But the idea is the Bouillon force multiply the distance x bar is equal to the moment, the total moment in this distance. But the right hand side is different. The right hand side is after we rotate, so there are some volumes going up, and there are some volumes emitted into the water. So the condition changes. So the change is the moment will equal to the total moment. The change in the moment in right hand side will equal to the total moment. So what are the changes? If you see here is a moment of the V before rotate. The moment before rotate should be equal to 0, right? Because it is stable. And the left hand side and the right hand side, the moment cancel out. As I mentioned, highlight here, if the volume to the left produces a negative moment, if the volume to the right here is produce the positive moments. So the idea is before rotate, the moment should be equal to 0 because of the balance. left and right moment cancel out. So this is always the volume because the moment is always equal to 0. But the later, the following the second items, why we use the minus here? Why we use the minus here? And why we use the plus here? If you take a look, there is AOB. The AOB is this area. The AOB. And this is EOD. This is EOD. The EOD is this area. As I mentioned, the volume in left-hand side is negative for the moment contributions. But in right-hand side is positive. So we know AOB is the volume located on left-hand side. So that's why we use the minus here. But this is EOD volumes is right-hand side, so we use the positive. And then you're going down and you see here, but the minus disappear. And here just tell you the small volume changes, and we multiply the distance xi, and then we do the summations, sum of the total moment contributed from the AOB areas. Okay, so but here why the minus disappear? Because if the volumes going up like this area, so what's the force we have? If the volume immersed into the liquid, we have the Bouillon force. But the volumes upgoing is above the water surface. So here we have the force is weight. We have the force is weight because it's not immersed into the liquid. So the AOB volumes is above the water surface. So the force is not the Bouillon force. The force is weight. The force is weight. So if your force is downgoing, and the rotated axis is is O here, so the moment in here should be counterclockwise. Counterclockwise, because your force is downward, and the 0 is rotation axis. So the moment in here is counterclockwise. The counterclockwise is a positive moment. So in here we just summation for the positive moment. And if you take a look, EOD, the EOD is immersed into the liquid. So the force is in here should be the upgoing, right? Because the Bouillon force, the volume is immersed into the liquid. So the force upward and the rotation axis is O. So in that way, the moment also counterclockwise. So in here also the positive moment after you rotate the shift. Okay, so that's why the two summations of the moments always the positive. And then we replace the summations symbol by the integrations AOB and the EOD. Okay, so and then here we would like to tell you what is the dV in integration part. The dV, as you see, this is a piece of the area dA, and if you know the height, this direction the height, so the dA multiply the height, and then you can have the dV. Okay, but how to compute the height? So because you know here is x, so the tangent alpha is equal to the x distance over height, right? So this height h, if we have the h and then multiply dA, so we have the dV. Okay, so the h is equal to x tangent alpha. And then you replace the h by the x tangent alpha. So the dv is equal to x tangent alpha dA. Okay, so that's why here use the dv is x equal to x tangent alpha dA. And then, so you just put into the integrations. So finally you can summarize final term like this. Okay? So, but this idea here, the equation didn't answer our questions. Our questions is we would like to know the CG and the CM distance. We would like to know the CG and CM distance. So if we take a look, we replace the integration part by here. But you take a look here, the difference is we do the integrations along the water line. We do the integration along the water line areas. So where is the water line areas? The first part is here. So we use the AOB, and the second part is EOD. And another part is the AOEIF. Where is AOEIF? AOEIF is here. It's here. And another is BODJH. The BODJH is here. So this is a total second moments for the water line area service. So, but I just tell you, for these equations, the final two terms, you don't need to take care, because for the pentagons, any pentagons, if the O is rotation axis, in that case, the second moment always equal to 0. So the final two is equal to 0. So you only have the final first two terms. The first two terms. But the first two terms is equal to the term of the total second moments here. Okay, so in that way we just replace this part by the I is the total moment. It's a total second moments when we consider the area is the along the water lines. Okay, and this tangent alpha is still here. So this is our final equations. X bar multiply the displaced volumes is equal to total second moments, and multiply the tangent alphas. So this is a total tangent moment. The second moments we already know the formulas. It depends on the shape of your panels. So it's depends on the shape of the water line areas. So if you know the water line area is a circle, so you can follow the second moment, the formula for the circles. If the right angle shape, so you can follow the right angle shape second moment equations. Okay, but again, our question is, can you just predict the CM? If you can tell me the CM length, and if we know the CG, and then just take the minus, and then we can identify the GM values is larger than 0 or not. Okay, so go back to our questions. So as you see, this is our final formulas. But if you take a look at the X bar is equal to the CM distance multiply the tangent alpha here, right? Because this is a CM distance, and this is a X bar. So we exactly know the X bar divided the CM distance is equal to the tangent alpha. Okay, so we know exactly the X bar is equal to CM distance multiply tangent alpha. and then we put the x bar go back to these equations here. So we can rewrite the equation showing here. And then the tangent alpha will cancel out because both sides have the tangent alpha. And then finally, we know, oh, the cm distance is equal to total second moments divided the volume displaced into the liquid. Okay, so if you cannot understand what I said before, but you need to keep in mind these equations. Because these equations, if we have the cm distance, and then we wondering to know, predict the gm distance, and then we can, based on the gm values, to predict the stability problem of the ship. Okay, so if you cannot understand the equations and the proof I showed before, but you need to keep in mind for the final equations. Again, so what is I? I is the second moment, but based on the shape you want. So where is the shape location? The shape is the shape cross over the water surface. Okay, for example, I put, this is a tank, and this is a water line, and I put the block, and the block is floating on the water, right? So what is the shape for the water line? The water line is the crossover areas on the water surface. So in this case, the water line should be right angle. Like this is the shape for the water. The crossover area for the water surface is right angle. So if the right angle surface area, so what is the I? We know the I is 12 over, maybe this is B and this is the A, and our rotation axis is along the A directions. So we know the second moment is A multiplied B 3 power, right? This is the second moment formulas for the right angle panel shape. Okay, so we exactly know the I, how to compute, and we know the displaced volume. Where is the displaced volume? Is here. Okay, so you have a displaced volume and you have a second moment, and then you can compute the Cm. And so the final is, how can we compute the Cg? The Cg is very easy, because because usually we assume our particle is symmetry. So the center of any symmetry particle is very easy to find out the centers. So we can easy to find out the C and G. So we don't care about the Cg distance. Okay, so if you know the Cm and the Cg, and you can compute the Gm value, and you can identify or you can predict the stability problem of the ship. Okay, so too complicated. So we just do exercise and try to figure out what is the ideas. Okay, so again, this is the wood and the 30 centimeters squares, as shown here. This is end view, and this is the side view. And so the cross sections is the 60 centers along the long axis, okay, and the total weight is 318 newtons. Okay, so the questions just would like you to answer the stability problems of the wood. Okay, but you take a look at the final answers. I just showing here not stable. Okay, along the longitude axis. In these directions is a longitude axis, right? In these directions. Okay, so I already tell you not stable. So we guess the answer for the GM distance should be less than 0, right? So right now we would like to calculate the true GM value is true less than 0 or not. Okay, so the first question is we didn't know the depth emitted into the water, right? We didn't know. The question didn't tell you the distance h. Okay, so our first question is we need to know the VB. The Bouillon force is upgoing, right? It's upgoing. This is FB. And we assume the liquid is water. And we need to multiply the displaced volumes. But we didn't know the H, so we don't know the true answer for displaced volumes. So here the gamma W and the length is 30 centimeters. So the 30 centimeters is 0.3 meters. And the distance along the longitude is 60 centimeters. So we multiply the 0.6 meters, but we didn't know the height, so we multiply the height. So this is the displaced volumes, okay? And because this block right now is floating on the water, so we assume the force is balanced. So how to do the force balance? Because we know only two forces along the vertical lines. One is weight, another is Bouillon force. So we make the balance is FB should be equal to W, right? We just make the force balance. So we can rewrite the equations gamma W multiply 0.3, 0.6, and H is equal to 318 newtons. Okay, so we can compute the H high. The H high is 318 divided the gamma W and divided the 0.3 and the 0.6. Okay, so we can compute the H high. And the gamma W here, because we assume the liquid is water, so we will use the 98110, right? 98110. So here 318 and 98110 multiply 0.3, 0.6. Okay? And then we can compute the answers for the H high. Okay, so use your calculators, and the answers is around the 0.18 this meters, so we can say the 18 centimeters. Okay, so now we know the height of the H. Okay, so we rewrite the idea here, because we know the H, so the distance in here is 18 centimeters. So you exactly know, first you need to plot the C, where is the C point, and where is the G point. Okay, the C point, the C is Bouillon's centers. So you only have these volumes here. So the Bouillon center in this plot, here is the C. Here is the C. Why? Because there's a total length is 18 centimeters, and only the volume displaced under the waters can contribute to the Bouillon force. So here is the 9 cms. It's a distance between the bottom to the C point. And where is the G? G is gravity centers. So we know the total height of the block is the 30. Is the 30. So the 30, the center of the 30, the center of the 30 is 15. 15. So the G maybe in here. Here is the G, and the G, the distance between the G and the buttons, the G and the buttons. So I just replot here. This is the C, and this is the buttons. So the distance between the C and the buttons is 9 cm, and here is the G. The distance between the G and the buttons is 15 centimeters. Okay, so in that way you can compute the CG distance very quickly. So what is the CG distance? The CG distance just 15 centimeters minus 9. So the CG distance is the 6 centimeters. So our question is we still didn't know what is the Cm. The m is the meta centers. So we don't know the Cm distance, but we know the Cm is equal to I second moment divided the displaced volume, right? So because we know the height 18 centimeters here, so we can compute the displaced volume very quickly. Just follow the equation showing here. So the volume, displaced volume is 0.3 plus 0.6, and multiply the 0.18, and this is our displaced volumes. So the displaced volume is equal to, use your calculators, is equal to the 0.0324 meter cubic. And the seconds, what is our second moment? Okay, as I mentioned, this is a block. So the crossover areas along the water lines, along the water line is the right angle. It's a right angle shape. So, and we know the axis right now we consider is longitude axis. So the longitude axis, the length is 60 centimeters. So the second moment is 12 over 0.6, and the width of the water line crossover area is 30. So here is 0.33 powers. As I mentioned, I emphasize, if the length parallel to the rotation axis, so the second moment, follow the second moment equation. Here is only 1 powers, but the perpendicular to the rotation axis, the power is 3. Okay, so you can compute the second moment here. Follow these equations. The second moment formula is depend on which shape you used. So in here is a right angle shape. Okay, so you can compute the second moment, okay, by your calculators. And so the second moment is equal to 1.35 and minus 10 minus 3 powers. Okay, and the unit is here is 4 power meters. 4 power meters. Okay, so we go back to here. The 1.35 multiply 10 minus 3 powers divided the 0.0324, and then you can compute the Cm distance. Okay, So divided the 0.0324. So the answers around the 0.0416. Okay, and the unit here is meters. So you just convert to the centimeters around the 4.17 centimeters. Okay, so as I mentioned, if you cannot remember anything, but you need to keep in mind the formula showing here. Okay, and you have the cm and you have the cg here. So as I mentioned, cm distance minus cg distance is equal to the gm distance, and we need to identify the gm distance is larger than 0 or less than 0, and then we can predict the stability problems. So follow our answers. First, the cm value is 4.17, right? And minus the cg is 6 here. So it's actually the gm distance is less than 0. So around the minus 18.83 around. Okay, so we say it's not stable because the gm is less than 0. So the key ideas, you only need to know the cm distance. For the C, and the second, you need to find out where is the C point and where is the G point. The G is center of gravity. The C is center of Bouillon force. Okay, so you need to pick out the C point and the G point first, and then you follow this formula. You can compute the cm distance very quickly, and then you do the minus calculations and identify it's larger than 0 or less than 0, and then you can predict the block stability problems. Okay, but after the rotations, yes, the previous questions, the block is not stable, so the block try to rotate, and after the block rotates, and then you see the question also would like you to tell us the block is stable or right now is unstable. Okay, so the answer tell you the block will be stable in these positions. So we need to recalculate the gm distance again based on these conditions. Okay, so again, how to compute? So first, we didn't know the W in here. We didn't know the W in here, right? So, and if we can determine the W length, and there is the triangle, so we know the height here is 2 over W. We know the height is 2 over W. So we know the volumes for the triangle in here. We know the volume for the triangle in here. So the triangle volumes, this is the triangle volumes, is W multiply the 2 over W, and the length of the wood block is 0.6 meters. So this is the triangle volumes. Okay, so we know the volume is 4 over W squared multiplied 0.6. Okay, but why I want to compute the triangle volume? Because we need to know what we need to know. We need to know the volume displaced into the waters. Okay, so the volume displaced into the water is equal to the total volumes the total volumes of the wood is 0.6 multiply 0.3 multiply 0.3 and then minus the triangle volumes. Okay, so here is 0.3 and multiply 4W squared. So in that way, because we can determine the volume displaced into the waters, so we can compute the Bouillon force. Follow this equation. We have the gamma W and then multiply displaced volumes, and then it should be equal to the total weight, right? So again, the total weight is equal to 318 newtons. Okay, so we can rewrite the equations. Here we have the gamma W is 9810, and then multiply the total displaced volumes here 0.3, 0.6.3, and multiply 0.3 minus 0.6 4 over W squared, and equal to 318. Okay, so you can follow these equations, and you can find the W length. You can find the W length first. Okay, so because the question showing here already tell you the distance. The distance for what? Because this is close symbol is the point C, and this is the gravity G. So the question already tell you the CG distance is equal to 5.73, right? The question already tell you. So, but the key questions for us is what is the CM? What is the CM? So first we need to know the displaced volumes, and we need to know the I is the second moment. So right now the I is different compared to the previous questions. So here the I, the closed water area, the length is W. So in our questions, for these questions, the second moment is 12 over 0.6, and the W in here 3 powers. Okay, and we know the moment. Okay, so because the time limit, so I just tell you, follow these equations, you can find out the W, right? And if you have the W, you can compute the second moment I. And because you have the W, so follow these equations, you know the displaced volumes here, VD. So you can compute the CM. So I just tell you the CM should be larger than 0. And then finally we can say in that positions the block is stable. Okay, so we don't have the time to finish, but the two equations. First one is here, and the second one is here. So, and the question already tell you the CG distance. So in that way, GM distance is equal to CM minus the CG. And the final answer should be larger than 0. And then you can tell us the block is stable right now. Okay, so CG is 5.73, and the CN you can follow this equation, compute by yourself. And the key parameter is width, W. So, but you can solve for the W. You can find out the solution for the W. Follow these equations. Okay. Okay. So this is our final slide for the chapter 3, and we have a 10 minutes break, and we will move to the chapter 4. Okay.